Hi everyone, welcome to the channel. In this lesson of continuation of classical encryption techniques, we are going to learn about Hill cipher today. Specifically, we are going to learn about Hill cipher encryption today, and in the next video, we will learn about the decryption process in Hill cipher. So Hill cipher is basically a multi-letter cipher developed by the mathematician named as Lester Hill in 1929. The meaning of multi-letter cipher is it encrypts multiple letters of the plain text. That is, it takes m successive plain text letters and substitutes them with m ciphertext letters. And Hill cipher is also a polyalphabetic cipher. The meaning of polyalphabetic cipher is in a monoalphabetic crypto system, each alphabet is mapped to a unique alphabetic character. But in a polyalphabetic cipher, it is a substitution cipher in which the cipher alphabet for the plain text alphabet may be different at different places during the encryption process. And so cryptanalysis is difficult for polyalphabetic crypto systems. Say, for example, if your plain text contains A, B, C, D, A, then and if the first A is converted into, if the first A is mapped to M in the ciphertext, it is not necessary that the last A also will be mapped to the same M. So different combinations of alphabetic characters may produce different alphabetic characters in the ciphertext. So the idea in Hill cipher is to take M linear combinations of M alphabetic characters in one plain text element and produce M alphabetic characters in one ciphertext element. Hill cipher is also a block cipher. So in block ciphers, the original message of M bits is broken into several blocks, each of N bits, where N is less than M, and each block contained is encrypted or decrypted using the same key. Okay, so the substitution in Hill cipher is determined by M linear equations, and each character is assigned a numerical value. These are the two things which you have to remember. So A is, for example, A is mapped to 0, B is associated with 1, C is associated with 2, and so on. Y is associated with 24, and Z is associated with 25. So Hill cipher has never been used much in practice, but the most important significance of Hill cipher is it was the first time that algebraic methods like linear algebra, modular arithmetic were used in cryptography in an important way. So say, for example, I told you that in Hill cipher, we take M linear combinations of M alphabetic characters. Let's say the value of M is 3. Then our entire cryptographic system can be expressed in terms of column vectors and matrices like this. I can say the encryption process as C is equal to KP mod 26, where C is your column vector representing the ciphertext. So here C1, C2, C3 represents your column vector representing the ciphertext, and P1, P2, P3 represents the characters of the plain text represented in a column vector. K11, K12, K13, K21, K22, K23, and K31, K32, K33 are the letters of your, or the representations of your key represented as a square matrix. So the basic formula which we are going to use in Hill cipher encryption is C is equal to KP mod 26, where C and P are the, C is a column vector representing the ciphertext, P is a column vector representing the plain text, and K is your square matrix. This K is a square matrix. It can be any type of square matrix. It can be a 2x2 matrix or a 3x3 matrix, etc. And this represents your encryption key. And its entries are integers mod 26. And also another important thing to note that we are talking about symmetric cryptography here. And so both the sender and the receiver are going to use the same key for encryption and decryption. And so the key matrix in the Hill cipher needs to have a multiplicative inverse, because when we use the key directly in the encryption process, we'll be using the multiplicative inverse of the key in the decryption process. And all operations are performed mod 26 in the case of Hill cipher. So let's learn about this Hill cipher with an example. Let's say our plain text is pay more money. So I need to make use of an encryption key. Encryption key is specified here. As I told already, encryption key might be generated by the sender and it might be shared secretly with the receiver, or it might be generated by a trusted third party. So here I have the plain text, which is pay more money. So how many letters are encrypted at a time depends on the key. If the key is a 2x2 matrix, it will encrypt 2 letters at a time. If the key is a 3x3 matrix, then the key can encrypt 3 letters at a time. So the basic concept is with a n cross n matrix, we break the plain text into blocks of n characters. So if you have a 3x3 matrix, we'll be breaking the plain text into blocks of 3 characters at a time, and we will change each block to a vector of 3 integers, and each of this vector of 3 integers will have values between 0 and 25. As I told already, we'll have all the characters of the plain text will be mapped to numbers from 0 to 25 for A to Z. So here we have the key K. Key is a 3x3 square matrix. So we have these characters in the plain text. Since we have 3x3 square matrix, it will encrypt 3 letters of the plain text at a time. So first I will take the first 3 letters of the plain text, PAY, pay, and I will encrypt it using the key K and produce the ciphertext. So as I told, each of the letters in the plain text, each of the letters in the alphabet A to Z will be mapped to the numbers from 0 to 25. So if you have a in the plain text, it will be mapped to 0. If you have B in the plain text, it will be mapped to 1. If you have C in the plain text, it will be mapped to 2. If you have D, it will be mapped to 3 and so on. So here in the plain text, I have P. So P will be associated with 15. The corresponding number associated with A would be 0 and the corresponding number associated with Y would be 24. So the column vector representing the first 3 letters of the plain text PAY would be 15, 0 and 24. Okay, 15, 0 and 24 represents the plain text letters P, A and Y respectively. So the next step is to do the encryption process. The formula which we use for encryption in Hill cipher is ciphertext is produced as the key K multiplied with the column vector representing the plain text, and then a mod 26 operation is also performed. So the formula is C is equal to KP mod 26. As I told already, we need to do matrix multiplication here. What is our key here? Our key is 17, 17, 5, 21, 18, 21, 2, 2 and 19. Okay, so we need to multiply the key matrix K with the column vector representing the plain text, which is 15, 0 and 24. So how do we multiply? We have to do a normal matrix multiplication here. Take the first row of the key K matrix, that is 17 is multiplied with 15. 17 is multiplied with 0 and this 5 is multiplied with 24, and all of the result will be added together and it will form the value in the first row of your ciphertext matrix column vector. So 17 will be multiplied with 15 plus 17 will be multiplied with 0 and this third number 5 would be multiplied with 24. Next we have 21 of the second row will be multiplied with 15. 18 of the second row will be multiplied with 0. 21 of the second row will be multiplied with 24. Next you have 2, 2 and 19 in the third row of the K matrix. So 2 would be multiplied with 15. This 2 would be multiplied with 0 and this 19 would be multiplied with 24. So since we are doing matrix multiplication, it also has to satisfy the condition for matrix multiplication. The condition for matrix multiplication is if you have to multiply two matrices A and B, the number of columns in the matrix A should be equal to the number of rows in the matrix B. Here we have 3 columns in matrix, first matrix, and we have 3 rows in the second matrix. So both these matrices are good enough for doing matrix multiplication. So here coming back, as I told already, we will be doing this calculation 17 into 15, 21 into 15, 2 into 15. And then we need to add all of those result, and then we have to do mod 26 operation on the result. When we do this, we would be getting 255. 17 into 15 would be 255. 17 into 0 would be 0. 5 into 24 would be 120. Same way, 21 into 15 would be 315. And 21 into 24 would be 504. In the third row, we have 2 into 15 would be 30, 2 into 0 would be 0, and 19 into 24 would be 456. Adding all of them together, we have 255 plus 120 would be 375. And we have 315 plus 504 would be 819. And then we have 486, which is the added result of 456 plus 30. Now we have to do a mod 26 operation here. So we need to do, here we need to do the mod operation on each of these elements separately. What is a mod operation? 375 mod 26 means it has to return the result of remainder of the division operation. So that means when you divide 375 by 26, what will be the quotient? The quotient which you get would be 14, and the remainder which you get would be 11. That remainder would be the value returned by the modulus operator. Okay, we are doing mod operation here. When you do 375 mod 26, then it would return the result of remainder of the division operation of dividing 375 by 26. 375 by 26 would be 14 as the quotient, and it will have 11 as the remainder. So the value here is 11. 819 divided by 26 will have 31 as quotient and 13 as remainder. So here it will return 13 here. Then for the third row, we have 486 mod 26. This will return 18 as the quotient and 18 as the remainder. So 18 would be the resultant value of 486 mod 26. Now we have to convert all of them back to their alphabetic mappings. So 11 is nothing but L in our alphabetic mapping. 13 is nothing but the value for N, and 18 is nothing but the value for S. So this is your resultant ciphertext for PAY. PAY, when you apply the encryption key for the Hill cipher algorithm, the corresponding ciphertext which you get is LNS. So this LNS along with the key will be sent to the receiver, and the receiver will be decrypting it on the receiver side by using the same key, and it will be getting back the plain text. So that is all about the Hill cipher encryption algorithm.